It's a new idea, relatively new idea, for building a new type of computer that can process information in completely new ways based on the laws of quantum physics. And quantum physics began more than a century ago and is very well developed and hasn't changed. But in the last few decades, we've come to understand that there's special powers that quantum machines can have that we simply didn't realize before. So a regular computer uses bits. They can be either 0 or 1. When you learn about the uncertainty principle, you can find out that quantum systems can be in states where you're uncertain what the value of something is. But why would I want to build a computer in which I'm uncertain whether the bits are 0 or 1? That seems like a bad idea. It's oversimplified, but there is some truth to that. And so that means you can do many things in parallel. You can consider the case that the number is 0 and the case that the number is 1 at the same time. And when you extend that to many bits, in this case, what we call quantum bits or qubits, you can sometimes do exponentially many things at the same time, and therefore carry out certain calculations that would be impossible on any traditional or what we call classical computer. Some people ask, does that mean that it's just that the quantum computer has a very fast clock speed? It can do many, many operations per second. That's not the answer. In fact, present rudimentary, simple quantum computers have clock speeds that are much slower than the fastest supercomputers. But as you make the problem harder and harder, if you're trying to deal with a larger and larger database or problem involving more and more options or variables, the degree of difficulty of that problem on a traditional computer can grow exponentially, can become very, very difficult. And it can grow more slowly on a quantum computer. So eventually, if you had a quantum computer that could deal with very large problem sizes, even though the clock speed is slower, the quantum computer would be much, much, much faster. There's tremendous progress being made every day in the quest to build large and useful quantum computers, but the technology readiness level is still very low. We're still in the very early days of this second quantum revolution, if you will. I like to say that it's maybe we've invented the quantum equivalent of the vacuum tube, or maybe only the abacus, or maybe the transistor. And the big quest now is to try to take the next step and make large-scale integrated circuits. So you should think of the state of the field as what it was for regular computers around 1940. Very rudimentary, simple quantum computers have been built with small numbers of qubits, and they work, but not well enough to really be economically useful yet. Although people are now able to access them online and program them and experiment with them. There are machines in the world that have approximately 50 qubits, maybe a little more. That doesn't sound like very many. I mean, my iPhone has billions of bits in it. But it turns out that you don't need a huge number of qubits in order to solve interesting problems. But those qubits have to keep their quantum information for a long time. And right now, they don't. So I described this extra power that quantum machines have that we're beginning to understand. that same effect that they can be in superposition states of both 0 and 1, the bits, quantum bits at the same time, is both a strength and a weakness. So weakness comes from the fact that these superposition states are very, very sensitive to tiny bits of noise or perturbations or interference from the environment. You need to be able to build better qubits which maintain their quantum nature for a longer length of time so that you have what's called greater circuit depth. You can run algorithms longer and longer time and still have the advantages of the quantum behavior. At Yale, the Yale Quantum Institute, we work primarily with superconducting qubits and superconducting microwave circuits. 20 years ago, when the first qubits were being built, they forgot their quantum information almost instantaneously, maybe in a nanosecond. And today, those times are beginning to approach fractions of a millisecond. It still doesn't sound like a long time, but the clock speed is fairly high, so you can do lots of operations in that length of time. But still, so it's the coherence times, these times that the qubits keep their quantum information, has risen by nearly a factor of 1,000,000 over the last 20 years. So there's been tremendous progress. And the way to do that is with quantum error correction, or to build circuits that are fault tolerant. That is, the challenge is to build a large collection of quantum bits, each of which is imperfect. But nevertheless, the collection as a whole acts nearly perfectly. And it's quite remarkable that in principle, in theory, this can be done. But we're still just at the beginning stages of learning how to do it in practice, in experiment. So that's one of the grand challenges for the field. It really took 50 years to get to today's supercomputers from the invention of the transistor. So to get to a massive completion of the quantum revolution might take 50 years. But there's so much intense focus on developing this new technology and so much interest that I think 10 years is long enough for us to make some significant progress, to see that it's possible to build machines that have economic importance. And of course, there'll still be 50 years of further developments beyond that in directions that we can't possibly predict now, I would say.